So, welcome everyone to the second week of the 2025 MTV Nuclear Engineering Summer School. My name is David Breitenmoser, a postdoctoral research fellow here at the University of Michigan, and I have the pleasure of moderating today's session. Before I introduce the speaker, please let me remind you again to use the Q&A chat only for questions related to the lecture content. Also, please kindly avoid using the raise hand feature, as question will be addressed during the dedicated Q&A session at the end of this talk here. With that, let me introduce you the speaker of today's session. For today's session, we are happy to welcome Sandor Katz, a first-year PhD pre-candidate in Professor Jovanovich's Applied Nuclear Science Group here at the University of Michigan. In his research, Sandor focused on characterizing the optical properties of novel opaque liquid scintillators, milk. If you're interested in his work, ask him later in the Q&A session. And now, Sandor, we are excited to have you with us today to discuss gamma ray physics and detection. Please, the floor is yours whenever you are ready.
Perfect. Thank you so much for that introduction. Okay, let me just share my screen again. Perfect, just pulling everything up. Perfect, awesome. Hello, everyone. As said, my name is Sandor Katz. I'm a first-year graduate student here at the University of Michigan. I'm working on scintillation detectors. Yes, I do study the optical properties of milk. It's a really cool characterization medium. If you ever want to learn more about it, please feel free to give me an email at the end of this talk. I love talking about my research. It's amazing. As said, feel free to put any questions in the Q&A webinar chat. And so today, the slides are adapted from Peter Hodvet, who was originally supposed to do this presentation, but wasn't able to make it today. Adapted from Kari and Lopez. So the topic is gamma ray detection, and we'll be exploring the concepts of gamma ray detections. This won't be as technical, going into the physics about how we detect gamma rays, more of a higher level look at these detectors. So a brief overview of this presentation. We'll be talking about the context and applications of gamma detection, looking at detector types and classifications, and then going into specific types of detectors. We'll be talking about gaseous detectors, so like Geiger-Müller tubes, scintillation detectors, that's what I work on, and solid-state detectors such as semiconductor detectors. So before we go into this, let's go back in time to the Greek god Uranus. And he is the Greek god of the sky, and then here's Gaia, god of Mother Earth. And so why are we going into this and about Tartarus, the infernal region of Greek mythology, the underworld in Greek mythos? Well, oddly enough, Uranus is, we have an element named after him, uranium, which we are quite interested in detecting. So it's a very important element for detection and also in nuclear power. And also just a fun little fact, we have a planet named after him. Now we have Hades, the god of the underworld, or Pluto, and we have another element named after this Greek god, and that is plutonium. So uranium and plutonium we're very interested in detecting for special nuclear materials, diversion, and also just knowing about dosimetry in general. So for the applications of gamma ray detection, there are many areas that we can go into, such as accident scenarios. So say you're at a power plant and you have a leak or a spill. If we have something radioactive that is leaking from our site, we will most likely be able to detect it via gamma rays. And if not, we can use some sort of other detector. Next, for source localization, so say some source gets lost somewhere and you want to localize it, we're able to use gamma ray detectors to hone in on those gamma signatures. And then also for in your home, checking radon. So in your basement, radon is naturally occurring and seeps through into your basement. So you want to make sure you're not being exposed to that radiation. So regular checks of your basement are important and need to determine if you need a radon mitigation system. Next, you can also do source characterization and safeguards for treaty verification. So it's important. So if a country has some enriched uranium, you want to make sure they're not over enriching it. So above 3 or 5%. So they're using it for peaceful purposes and making sure that what they're saying it's being used for is actually being used for that purpose, and make sure it's not being diverted or going to non-peaceful applications. Next, gammas are also important for radiotherapy, so for cancer patients, and also medical imaging. We're able to use these to help in medicine, so it's a very broad field. And finally, of course, space. So say we have a gamma ray burst from space, we want to understand where it comes from. It helps us to understand the galaxy and also light, photons, detecting those. We're able to use that in space applications as well. Next, so how are we able to detect these gamma rays? We're able to detect these gamma rays through multiplicity of different processes. But in general, for radiation detection processes, we can kind of split things into two different fields of directly ionizing radiation and indirectly ionizing radiation. So for directly ionizing particles, these particles have charge. So you can think of alpha particles, beta particles, which is an electron, and heavy ions. So when they interact with a material, they directly ionize it. So if you have a Geiger-Müller tube, if you have that heavy directly ionizing particle interacting with it, it'll come into that gas, knock off an electron from an atom. So you have this electron-ion pair. So you're able to use these electron-ion pairs to detect that some radiation has interacted with your detector. And then with a solid-state detector, you're able to use an electron-hole pair. By that, I mean a solid-state detector is a crystal lattice. So when a particle comes in and knocks off an electron, you're left with a hole as everything is contained within a lattice. And that electron is able to freely move, and you're able to use the electron for detection to detect that some sort of ionizing radiation has interacted within your detector. Next, for indirectly ionizing particles, we need to have they go through some nuclear reaction or different mechanisms in order to ionize that material. So for neutrons, they can hit the nucleus of a particle, knock off a proton, and then that proton can go through your detector, ionizing the gas or the solid. These do not have charge, so you need to rely on secondary charge particle interactions to get that signal. Yeah. So as said, yeah, they can create those secondary charge particle interactions. And so when we get these electron ion pairs, electron hole pairs, we're able to create an analog signal, so an electric current. And from this, you're able to take the electric current, read it out with something like a digitizer, or think of it as a multimeter, and you create a digital signal. And from there, you're able to get the energy of the interacting particle, the time it interacted within your detector, the particle type, and also you can find the interaction type that occurred by looking at different spectrum. And so what you get out is from the signal is essentially a waveform of the amount of charge deposited in your detector. And so the way that this charge is deposited in your detector so are through different photon interactions within the matter. And here's just a general list of different photon interactions that can occur, but we're really interested in these big three interactions here. So the photoelectric effect, the Compton inelastic scattering. So when a photon scatters off an electron, and then an electron, the electron in the outside of the atom is flung off and then is able to go through the detector, and then pair production where a gamma is absorbed and then you get a electron and a positron produced. So these are the three main interactions we are interested in when we're doing gamma ray detection, as they're the easiest to detect. Whereas these are very low energy and it's very difficult to see them. And so for these interactions, you can get something called a total photon cross-section. So that's kind of the probability of interaction. So these interactions have different probabilities depending on the energy and the Z of your material. So say we have lead, which is 82, and at these Z of 82, so number of protons. And so when you have a low energy photon interacting, it'll be more dominated by the photoelectric effect. But as you get to these higher energies around 1 MeV, Compton scattering begins to dominate. Of course, photoelectric effect can still occur, but it's dominated by the Compton scattering. And as you get to higher energies, around 10 MeV, pair production occurs. And so when you put these all together, you get a plot of the total interaction cross-section. So you see that at these lower energies, so it's the probability of this event occurring. So how likely is it for a gamma to undergo Compton scattering? We can see that at lower energies, the photoelectric effect dominates. And then here around those mid energies, Compton scattering dominates. And then at those higher energies, pair production dominates. And then here is just the total cross section, just all three of these added together. And so it's very important to understand the material in your detector so you know how gammas are going to interact with it. And also, if you're trying to detect another particle, it's important to know how that particle will interact in your detector because it's all about energy deposition. So some of the detectors we'll be talking about today, the three we'll be mainly focusing on are scintillation detectors, semiconductor detectors, so you can think of high purity germanium detectors, and ionization detectors such as Geiger-Müller tubes. Some other detectors that are cool, just to note, are chemical detectors, so photographic emulsion. So that's essentially like a film. So you can think about taking a picture with a film camera. You have activation detectors, so that's your dosimeters that we wear within the lab. And then we have luminescent detectors that are optically stimulated. And so the first detector we'll be looking at is the ionization detector, or the one I really like to look at is the Geiger-Müller tube. And so, so we'll be talking about gaseous ionization detectors. And a really cool visualization of this is the cloud chamber. And here we have a uranium rock within the cloud chamber. And we can see all these ionizing particles coming off this uranium rock. So how is this working? A cloud chamber works. It consists of a sealed environment containing a supersaturated vapor. It's usually alcohol. And so with this vapor, you're able to, with this vapor, energetic particles, for example, alphas and betas, which we're seeing in this image, knock off electrons from the gas molecules. And then when this occurs, condensation forms at these points, so resulting in a trail of ionizing gas particles. So what you're seeing is the gas condensating along the trails of the ionizing particles. And so you get like a mist-like trail of small droplets that form in the gas mixture. And these droplets are visible as a cloud as they condense. And these tracks have characteristic shapes. So for example, the alpha particles, they're a straight track. They're very thick and straight, while beta particles are a little bit more wispy and show evidence of deflection by collisions within the medium. So I'll pull up an image of one. So this is an image of a track. So say we have a gamma come in and a gamma enters, and at this interaction origin, absorbed, and we get pair production. So, but it does it off a recoil electron. Recoil electron, perfect. Pair production with recoil electron. And we can see here without an electric field that this electron and positron will begin to spiral and go into these little coils. But if we apply in a magnetic field, which we do in a cloud chamber, we see that when the gamma comes in and pair produces with an electric field, that we can control the path of these ions and get these straight tracks. And so in an electric field, in ion chambers, we have an electric field. So the principle is that it's a gas-filled space with two electrodes supporting the electric field. So we have an anode, the cathode, and we have some DC voltage being applied. When the gamma interacts, it creates charged particles, and we get this line of electron-ion pairs along the track of the gamma as it goes through the detector. Now, as these charged particles move through the gas due to the electric field, they induce a current. So you're able to see, read out the current of the detector and see that some gamma has interacted in it. So this migration and collection of charges is how we know if a particle has interacted in our detector. So it's all about charge collection. And we're able to change this voltage in order to change the amount of electron-ion pairs generated, as well as how quickly they, as well as the multiplication of these electron-ion pairs. And so within an ion chamber, there are usually three regions. You have the ion chamber region. So this is where they're proportional. As you increase this voltage, the alpha and beta counts will stay constant. But then when we get to this proportional counting region, as you increase that voltage linearly, the charge collected increases logarithmically. And so this is very helpful. So you get that proportionality in this region. In this limited proportionality region, it's not really helpful because as you increase the voltage, you don't really have proportionality between alpha and beta, so it's not very helpful for our purposes. And then finally, we have the Geiger region, which is a very sensitive region, and you're able to measure both. This is, yeah, so the Geiger region, the alpha and betas will cause a avalanche. So the same amount of charge will be produced per alpha particle interacting and per beta particle interacting, no matter what. And so these are very useful in the field. And if you haven't heard one before, this is what a Geiger-Muller counter sounds like. And so this clicking sound that you're hearing is the electrical discharge of ionizing particles interacting within the detector, and you're getting those electron-ion pairs drifting to the anode and cathode, and you're getting that electrical discharge. And so the way these detector works is by avalanche formation. And so in these detectors, they're quite high voltage. They use high voltage, so it's a couple thousand volts. When ionizing radiation comes in and you have an ionization event and you get an electron, these electrons will be accelerated towards that anode wire. And as they accelerate, they can go through and begin to slam into other particles and ionize those other particles, thus creating a cascade of electrons. And so as these electrons then cascade, they can also create photons. And these other photons can go through and then ionize the detector, ionize the gas and produce other electrons, which produce more cascades, and so on and so on and so on. And this is why we get such a large electric signal per one incident particle of radiation interacting within the detector. And what's really cool is that we can get about 10 to the 8th to 10 to the 10 electrons from this detector. So you're able to read this out with almost any electronics or even a microphone. So as you could see or hear in the last slide, that was the electrical discharge. So it's very easy to get the output from these detectors. And so next we'll be talking about scintillation detectors, which are my personal favorite. Excuse me. Scintillation detectors. And scintillation detectors fall into two main categories. We have organic scintillators. So scintillation light is emitted when a ionizing radiation comes in and deposits energy. These are usually mostly made up of carbon and hydrogen. They're low density and low Z. Inorganic scintillators use crystal lattice. You can think of plastics. They're usually plastics. They're high density, high Z, and so inorganic, you get the free electrons, as I was saying. The free electrons in the crystal lattice are what allow you to produce that scintillation light. And so the detection principle of these is, this is a simplified detector, is you have a gamma ray coming in, interacting with the scintillator, and when it deposits energy, you excite the scintillator, and when the scintillator de-excites, it emits an optical photon. So this optical photon travels to a photomultiplier tube, and on the top of the photomultiplier tube, it has a photocathode. This photocathode is able to convert incident photons into electrons. So you have a photon to an electron. And then as that electron drifts this tube, which has an applied high voltage and electric field, as it hits these multiplying stages, the electron begins to be multiplied further, further, and further. So then you're able to get a readable signal by multiplying electrons. And so thus we're able to convert ionizing this conversion of light to electron to give us a readable signal. And the energy deposition for different ionizing particles interacting with the detector differs. So you're able to use these scintillators to tell, say, if a gamma interacted or a neutron or an alpha interacted in your detector. And so the de-excitation process is called luminescence. And so that's when you're able to convert the energy into visible light. Yeah. And so organic scintillators, as I said previously, are made up of two elements, mainly two elements, such as which are hydrogen and carbon. And using these two elements, you're able to create light. And so we have two types of light fluorescent luminescence mechanisms with different time behaviors. So with fluorescence, it happens on the scale of nano to microseconds. So this is very prompt. It's almost instantaneous. So when the particle comes in, it excites an electron to a higher singlet state, and then it immediately decays and is able to either emit a photon or get rid of the energy through heat. So this is a direct transition, so it's very quick and prompt. And however, there's something called intersystem crossing. I won't go over why this happens, but this causes the state to change to a triplet state. And so this triplet state undergoes phosphorescence, which is delayed and takes about a couple milliseconds to decay to the ground state on the scale of milliseconds to the ground state. And so this slow decay, we're able to see it in the output of our photomultiplier tube, and we're able to tell the difference between different particles interacting, because as I said, different particles deposit energy in different ways. And so this is what it looks like when an alpha, a fast neutron, and a gamma ray deposit energy. So we can see here that this is the light intensity, and then this is the time of arrival of that light intensity. And so we can see that they have this same prompt signature, but the tail is different between these three particles. And so the difference is, by the way, gammas don't fill those triplet states as frequently as fast neutrons or alphas. So that's why we get this shorter tail. And so using the ratio of the area under the tail compared to the area under the total waveform, we're able to get something called pulse shape discrimination. So finding that tail over total ratio, we're able to discriminate between neutrons and photons. And this is important for, say, nuclear nonproliferation, if you're trying to see if there are neutrons present in the background, which could indicate the presence of special nuclear material. And so for scintillators, we want them to be low density and low Z, low density and low Z scintillators have low gamma detection efficiency, which is mostly Compton. So you really want a something with a high Z and a high density in order to detect those gammas. But for neutrons, you want the lower Z in order for them to more easily interact within the detector. And so the types of organic scintillators we have are first plastics. They're extremely fast, 2 to 3 nanoseconds for their signal. They're very flexible, so you can have them in sheets, blocks, fibers. I mean, the world's your oyster with them. Then you also have liquids. Again, they're quite fast, 3 to 4 nanoseconds. And what's nice about liquids is you can load them if you're trying to also look for a different particle. So you could load them with lead if you wanted to, if you want. But these liquids are very sensitive to impurities. So if you don't properly load them, that could impact your performance. So that's something you really need to think about when you're dealing with liquid organic scintillators. And then also you have organic crystals such as transstilbene. They're a bit slower. Transstilbene's pretty fast, but they're going to be a little bit slower. Anthracene is 30 nanoseconds, so that's a little bit of a slower scintillator that we have. But they have a very high light output, and anthracene has the highest light output of all organic scintillators. They're very durable, but very difficult to handle. So next, now we've gone over the basics of organic scintillators. We'll talk about inorganic scintillators. So the scintillation process in inorganic scintillators is based on the behavior of liberated electrons in a crystal lattice structure. So that's the band gap model. So we have a electron in the valence band, and you need enough energy to bring it into the conduction band in order to ionize the material and create an electron-hole pair. So these materials typically contain an activator, so that's some impurity, creating an intermediate energy level in the band gap, allowing those electrons to be more easily freed. And so when the electron moves from the conduction bands, it's captured in luminescence centers. And so we're able, so when that electron decays, it's able to produce scintillation light. So that scintillation light, those photons, we're able to convert to an electric signal and detect that ionizing radiation has interacted with our detector. And so an example is of a inorganic scintillator being doped with some other material is thallium and a sodium iodide detector. And so a couple more examples of crystals is zinc sulfide. It has a high efficiency. Those actually, you can see the scintillation light by eye. So Rutherford used these in his experiments. But the problem with that is if you can see it by eye, it has a long decay time. So it's not prompt. So that's not something you want when timing is of concern. And then for sodium iodide, you have a quick decay time. It has a high Z, so it's a very good gamma ray detection efficiency. However, it's difficult to handle. It's sensitive to moisture, so you gotta protect it and make sure you take care of your crystal. But it's very commonly used. And then we also have cesium iodide. It's similar to sodium iodide, but it's a little bit easier to handle. It's less susceptible to thermal and mechanical shock. It doesn't have the issue with the sensitivity to moisture. However, it's very expensive because the materials aren't as easy to source as sodium and iodide. And so some uses of these crystals is in barium fluoride barium fluoride, yep, which is a very fast scintillator, so it's 700 picoseconds, but it has a low light yield. BGO, very high Z, good for high energy photon absorption, and doesn't have the issue with moisture. And also we have lead tungstenate, and this was used at in CERN on ALICE. It's called a Large Ion Collider experiment at CERN to study PB lead-lead collisions at CERN. Yeah. And it's faster than BGO. And just briefly, these crystals are grown. So what happens is you have a little dish, and the crystal is slowly grown in a dish, so it's inorganic. And then they're machined down, encapsulated in usually an aluminum housing, and then attached to a PMT. So with this, we're able to seal out any of the room light, so that way we don't have background affecting our measurements. So we're only getting counts from energy or from ionizing radiation within the detector. And so again, so yeah. So an example of what a output spectrum would look like. So say we have a radioactive source next to our detector, let's say cobalt-60, and we want to understand the source, so understand the energy of photons being emitted, or gamma, sorry. We put it next to our detector, and we get this output spectrum. This is called the gamma spectrum, and we can see here that we have two peaks right here. And these peaks are caused by the photoelectric absorption of the 1.1 MeV and 1.3 MeV gamma rays emitted from cobalt-60. And we can see here right now, the red is the sodium iodide detector, but here's the germanium detector. And we can notice something a little bit different, that the germanium, you just get a little bit of a spike. Whereas the sodium iodide is more of a broadened spectrum. And we'll go over that a little bit later. But that's just a cool feature you can see. And then also you can see the Compton continuum of the cobalt-60 source. Here. Next slide. Right. So when we're looking at that plot and we're looking at those photo peaks, we saw this kind of broadened effect that looked like a Gaussian. So detectors have different capacities to distinguish between interactions of different energies. And so the way we characterize this is by looking at the full width half max of a peak. So that's just looking at the maximum of the peak and then looking at the, oh, able to see it now, perfect. Looking at the maximum of the peak, then going to half max, and then looking at the distance between the edge. So you're looking at the width of that peak or of that Gaussian curve. And so so this tells you how well you're able to distinguish between interactions and also different energies, and this helps you with spectroscopy. And so we have for scintillators, there's a wide range of energy resolutions per charge carrier. So usually for scintillators, you have like about 2 to 500 EV per photoelectron, or it takes 2 to 500 electron volts per photoelectron to liberate an electron. Whereas with gaseous detectors, you have about 30, it takes about 30 electron volts for 1 electron ion pair. Whereas with semiconductors, about 3 to 10 electron volts. So you really want that the energy to be as low as possible so you have the most amount of charge carriers. So as you increase the number of charge carriers, you're increasing the amount of information you have about the incoming radiation. And so we can see here with the scintillation detector with our much higher energy to liberate an electron, we see it's very broad, but with the solid state detector, it's very, very narrow, very peaked, and we don't see as much broadening. And this is because we have much more information coming in per interaction. That's because we're able to liberate electrons more freely from the surrounding material. And so as you can see, again, no broadening, you're able to better distinguish between those two energies. And so if your energy resolution decreased, say for the sodium iodide, those two peaks could overlap and you wouldn't be able to, distinguish between the two or understand that there are even two different photons interacting. And so now let's talk about the germanium detector, which has these very nice peaks for gamma spectroscopy. And so the basic principle of a semiconductor detector is you have a crystalline structure in the material that allows for energy bands. And between these two bands is called a band gap. So that's the energy spacing between the valence band and the conduction band. In the valence band, electrons are not able to freely move, but in the conduction band, electrons are able to freely move. So when ionizing radiation interacts, electron hole pairs are formed and are our primary charge carriers. So when an electron is liberated from the crystal, it just leaves a hole behind. So it's kind of a false positive charge. That's kind of our placeholder for that positive charge. And so to generate that electron hole pair, the photon must deposit a minimum energy of the band gap in order to raise that electron up to the conduction band so it does not fall back down to the valence band. And so you can think about it as Homer Simpson trying to shoot the gap. And so if he doesn't have enough energy, he's just going to fall. He's not going to make it to the other side. But if he has enough energy or an excess of energy, he's going to make it all the way to the other side and then some. So you can think about it like that. So you need to have a minimum energy to make it to the other side in order to form those electron hole pairs. And so to increase the amount of charge carriers, you want to decrease this band gap size. So that way it's much easier for ionizing particles to bring electrons into that conduction band, and so you get a better signal. However, the problem with this is thermal fluctuation. So thermal energy can allow these electrons to jump from the valence band to the conduction band. So you need to cool these detectors to about 70 Kelvin using liquid nitrogen. Otherwise, the thermal excitation will just, will just kill your detector. You won't get any useful signal out of it. And so high purity germanium detectors, there are different types. They all have different types of cooling. There's liquid nitrogen, somehow have even built-in coolers. But yeah, that's something you really need to think about when you're using a high purity germanium detector, and also does that fit your application as well if you need to cool your detector. And so the types of semiconductors within this solid state detector, first you have intrinsic detectors. So this is an ideal case where the number of electrons equal the number of holes, but this is very hard to achieve in the lab or in the real world. And so with any impurities, if the number of electrons does not equal the number of holes, your detector just isn't going to work. So what we do is we use a N-type, which has a donor electron. So that means the energy level is raised up closer to the conduction band, so electron is more easily able to be freed. And then a P-type semiconductor, where it has an acceptor level, so it's able to accept an electron very easily. And so when you're doping the material is introducing impurities to make it easier to jump this gap. And so this really depends on the electron valence in the crystal structure. And there's a lot of materials research being done on the detector properties and materials to really, decrease that band gap as much as possible so you can have the highest signal possible. And so some common semiconductor detectors we have are, as I was saying, the high purity germanium detectors, which are the gold standard of semiconductor detectors. So you can achieve an energy resolution of 0.2% for cesium-137 for that 662 keV photon. And then, however, again, as I was saying, they must be cooled to cryogenic temperatures. Peter's research was on CZT detectors, which are room temperature semiconductor detectors. And so they're able to operate at room temperature without that significant thermal noise. So you don't need to be cooled, so you don't have that as much thermal excitation. And right now, they're more like 0.7% energy resolution at that 662 keV peak. But they're able to approaching 0.3% energy resolution in research settings. However, the reason why they're not more widely used is they're expensive to manufacture, the materials are rare, and the crystal is difficult to grow. And so some final remarks on gamma detectors. One must consider why are we building this detector? So the application you have in mind is very important. So are you trying to identify a material? Are you trying to quantify how much there is? Are you trying to monitor something? Or are you trying to look for something that you don't know is there? Is it for research? So the different applications you have in mind are important for what detector you want to use, where you're going to be using it as well. And so you also want to understand source characteristics. So the energy of your source, the activity, the composition, because all different if you're looking for, say a neutron emitter versus a gamma emitter, you're going to want a different detector for that, or a detector that can detect both. But, what trade-offs are you going to get with those detectors? So that's very important. Then also the geometry, how big or how small do you want it? If you say you're putting a detector in space, you want it to be as small as possible, but also if you decrease the active volume of your detector, well, then you're not going to have as many interactions. So you really got to think about what's the size of your detector, where are you going to put it, and then also like how much of it do you actually need? Because if you just make the detector arbitrarily large, well, then that doesn't do anything for you. It just kind of wastes money if you could optimize it to be a little bit smaller. Also, you want to think about your detector materials. So what's your Z effective, the light yield, your charge yield, decay times. Do you need fast timing? Do you need slow timing? Or like how? And this timing depends on, your source, the activity. Also your amplification, how much signal do you want out from it? Also, your signal, what's your dead time, your saturation. So dead time is, if you have a high source, if you have a very active source, your detector isn't able to recover fast enough, you're going to be missing counts, and which is not good. So you really need to understand which is affected by decay time. So you need to decrease your decay time. So that's very important to understand. And then also electronics, for your output electronics, how much data do you need? Because if your scintillator has a decay time of 1 nanosecond, but your electronics are collecting a pulse every 10 nanoseconds, you're not going to be able to get that timing resolution you want. But also, how much data are you transferring? Are you going to be able to, reasonably transfer the data from your digitizer your computer. So that's also very important to think about. Again, digitization, read out how are you getting the information from, an electronics point of view to a readable point of view for yourself, and also cost and utility. You don't want something very expensive that you aren't able to use in the field. And finally, wrapping up the talk on kind of with the theme of Greek mythology. So in academia, we have here the School of Athens, painted by Raphael in the Vatican. We have Plato and Aristotle. They're academics and they're learning from each other and they're talking to each other. And we can see that they're holding two books. And one might wonder, what book are they reading? Well, if we zoom in and look, we can see that they are reading Radiation Detection and Measurements by Glenn Knoll, who is a Michigan alum. It's the Bible of nuclear measurements. All the information I've read through part of this book. It's a very, very easy to read book. Even coming into it, he does a great job of explaining the concepts, the physics. So if you ever want to know more about radiation detection and measurements, this is always a good place to look. I still go look into it when I need help in the lab. It's a very good thing to have at your side if you're interested in detection. And also, if you'd like to know more, I'd be happy to answer any questions. If you'd like to email me about my work, I'd be more than thrilled to talk to you about it. Finally, just fair use disclaimer, bibliography, of course, image attributions. And yes, thank you so much for your attention today. I really appreciate it.
Thank you so much for the great talk, Sander. We'll now move on to the Q&A session. If you have any questions left, please type them into the Q&A chat. I will go through them and read them out for discussion. Let's start with the first question, and this is referring to slide 8, Sander, where you showed the cross sections of the different interactions of gamma rays or photons with the material. So there were a couple of questions regarding these interesting edges we see at lower energies. Can you maybe elaborate a bit more on these edges, how they are generated?
Yeah, so I'm assuming you're talking about these little edges here. Okay.
Exactly.
I'm racking my brain. Here we go. So this is due to the different energy shells you have in an atom. So it's the K, L, and M. I believe it's K, L, and M shells you have on an atom. So as you move towards those energies and you get to a high enough energy that you're able to go into the next band, lower band, and liberate an electron from that one, your cross section increases. So this just has to do with how the atom or the electron shells are made, or like the energy needed to free an electron from the shell.
Great. Next question. You demonstrated or briefly mentioned these different interaction mechanisms, but focused on the three main ones we see here on this slide. There was a question about if there is any application for elastic scattering in radiation detection. And I might add here as well, do we have other interaction mechanisms we can exploit for, let's say, more niche applications you're aware of?
So for elastic scattering, it's just you don't get much energy deposition. It's very low energy deposition. And for the energies that we're interested in, as you can see in the other plot, these are really the ones that dominate in the photon energy ranges that we are going to be looking at. So we're not really going to be going below a couple keV. So photoelectric is dominant at those energies. So, and above that, you're going to be dominated by Compton scattering and pair production. So that's why we kind of have these big three. And then for other interactions that we could, can you repeat the second part of the question? Sorry.
Yeah, it was only me curious if any of the other interaction mechanisms are maybe exploited in some niche applications, like for example, photonuclear reactions, if we think about high energy applications.
With the new
The whole thing.
I haven't done much with photonuclear interactions, so I'm sorry, I'm not able to answer that.
Okay, then let's go on to our next question. And this is referring to the photomultiplier tubes. You briefly mentioned there that we turn these photons to electrons and then multiply the electrons. Maybe for some context for some folks, can you give or elaborate a bit more on that?
Yeah, let me pull up the photomultiplier tube real quick. Here we go. Where'd you go? Base. Okay. Yeah, so for the photomultiplier tube, so what happens is, so you have a thin film, it's a very thin film, called a photocathode. And so when you have a gamma ray that interacts within your scintillator, and you have a photon, so a visible photon, such light you can see, is emitted from this interaction from, say, a electron from ionization, and it interacts with that photocathode. The photon is absorbed by the photocathode. And so when that photon is absorbed, it's able to deposit its energy within a photocathode. And so it's also kind of like this band structure. So you're able to raise electrons up to an energy level. And the way the energy levels are designed is that when an electron within the photocathode is raised up that level, it's able to, it moves into the photomultiplier tube because the energy level of the photomultiplier tube is lower compared to the conduction band of the photocathode. So it moves from that high energy to low energy. So when that photon's absorbed, it raises an electron to a higher energy state. And then because the photomultiplier tube has a slightly lower energy state, it's able to move into that photomultiplier tube. And then from there, there's an electric field. And this drifts the electron into these multiplying stages. So when the electron slams into this multiplying stage, it has like some multiplication for each stage, and you have a certain number of them. So when it slams into it, it'll multiply it by, say, 6 times each time. So when one slams in, it'll multiply by 6. And then for each additional, then all those electrons now are being accelerated to the next stage. And then all those electrons get accelerated. So 6 times 6, 36, 36 times 6, to the next stage, into the next, to the next, to the next, to the next. And then you generate all these electrons, and you're able to create that readable signal. Does that answer the question?
I think so. Thank you so much. Then we had some interesting questions regarding pulse shape discrimination. The first is referring to machine learning. I will read it out here. In light of the fundamental interaction mechanisms covered in this lecture, how might convolutional neural networks be leveraged to enhance pulse shape discrimination in various scintillator detectors without compromising real-time throughput?
I haven't been working on neural networks myself. I wish that some other people in my lab group were here today. They'd be able to help you with that. But we are working, there are some like neural networks that are we're working on to help with discriminating between pulses that have very small differences in the tail. So you're able to get PSD from, say, scintillators that normally you wouldn't see that in. And also you can look for different characteristics, say possibly even in the rising edge of the pulse, which is, we're looking, nothing yet, but possibly.
All right. So stay tuned, I guess.
Yeah.
Then one other question is in regards of this PSD. So I think not all of our attendees are familiar with this concept. So maybe you can briefly reiterate how this actually works. Why do we have these different bands for neutrons and gamma rays here?
Yeah, so we have these different bands. It's about how the energy is deposited within your detector. So it's how you can think about, so it's how easily they'll populate those triplet states. So when you have energy very densely deposited, such as with an alpha, whereas kind of a gamma ray will tend to scatter through a medium and the energy is more deposited over a larger area. When at least this is my understanding, that causes triplet states to be more easily populated. So it's about how energy is deposited within the detector for these different particles. So they all interact in different ways. So as they deposit that energy, they all have different interaction mechanisms. And so those mechanisms by themselves populate those triplet states at different rates. So if you know what So you're able to calibrate your detector with a neutron, a gamma ray, and an alpha source. You're able to kind of understand the rates at which those triplet states are populated and understand that delayed component of a light emission.
Interesting. Next questions refer to energy resolution.
Mm-hmm.
I will start with a more broader question. So, which factors determine actually this energy resolution of scintillator detectors? And how could we improve those? Or is there any way we can exploit maybe some techniques to improve this energy resolution?
Yeah. So the energy resolution again is just like how much energy is needed to liberate an electron for an incoming or it's determined by that per an incoming photon or ionizing particle. And the way well, semiconductors are much easier to liberate because of this the smaller band gap. So I don't personally work on the side of narrowing the band gap, but I would assume there's probably work into looking in how to narrow the band gap between those conduction and valence states. So that way, the amount of energy needed is lower to produce a photon.
Mm. And then there was another question specifically to HPGEs. So, which kind of fundamental processes there dominate actually this energy resolution? The attendee is explicitly referring to collection efficiency and electron noise. So maybe you can talk about a bit the electronic side, right?
Yeah.
So not only the intrinsic resolution.
Yeah. So on the electron, so what's great about, well, as I was saying earlier, you need to cool these detectors because of that thermal fluctuation. Because when you have particles, when they're warm, they vibrate. And so those some electrons may be able to shoot that band gap, excuse me, and make it to the other side without even having ionizing particles interact. So by cooling the detector, you're reducing that thermal fluctuation, and so you have a very low noise of, electrons. Of course, some electrons will still populate that conduction band, but it's very small amounts. So you get a small signal from the background. And the way these detectors work is when you have your N-type and P-type semiconductors, they're pressed up together. And what you do is you bias the detector, so reverse bias. And what happens is you're trying to drift any free charges you may have within your detector to the two ends, so that way you have open or so that way in your detector it's available for incoming ionizing particles to knock off an electron. And then you need to have your bias voltage, so the voltage applied across this N-type and P-type conductor must be high enough such that it doesn't get stuck in a hole. So as that electron drifts, you want to make sure your bias voltage is high enough so it doesn't go back down into the valence band. And so you're able to drift charges across your detector and get that signal. So as the charges populate into that conduction band, drift to the edge, and you have these plates at the end, an anode and a cathode. And so when that electron hits your anode and cathode, kind of like a photo, the Geiger-Müller tube, that creates a detectable signal for you.
Great. Actually, there was another question regarding the cooling of these HPG detectors. So how are they actually cooled, or can we use their different methods to cool these detectors?
Yeah, so there are actually a bunch of different methods to cool the detector. So one detector I was able to use in one of my classes was a handheld detector about this size, and it had its own built-in cooling system. I'm not sure what the cooling system is, maybe some piezoelectrics. I'm not too sure. That may be incorrect, but it had its own built-in cooling system. So you kind of have you can have like a condenser with your detector or a cooling system. So like in our lab, we have a couple detectors that we can hook up to an external cooler, and it runs a fluid through the detector that keeps our HPG cold. And then for the liquid nitrogen detector, you have a dewar. So it's just a big cooler essentially. and you fill that with liquid nitrogen. And then what you do is you dip in an aluminum or a tube into it. And so that connects to your detector or a metal tube. And so that thermal connection between the HPGE detector, the aluminum tube to the metal tubing to the liquid nitrogen is able to keep your detector cold. So you're not actually submerging the detector into the liquid nitrogen itself. You're more using it's called a thermal finger to cool your detector.
Cool. Another question referring to a new concept, which are diamond detectors. So what can you say about diamond detectors for gamma ray detection? Have you ever worked with those kind of detectors?
I have not. I cannot say anything about diamond detectors, unfortunately.
Oh, fair. Okay, then we have to address at this point here again to the literature. Other question, what about semiconductor photodetectors? Can you discuss the current trend in the use of PMTs against semiconductors? I guess the attendee is referring here to the SIPM. So can we, what are the advantages of these readout systems?
Of SIPMs compared SIPMs, silicon photomultipliers compared to PMTs?
Yeah.
Well, personally, I'm a big fan of silicon photomultipliers. So just for everyone who may not know, so when a photon comes in, it deposits its energy into this semiconductor, and it frees an electron. You're able to get electric current. What's really nice about SIPMs is they're small. You don't need a large bias voltage. They're small, not a lot of bias voltage, and also not affected by magnetic fields, which is nice. So you're able to get a lot of them together. However, the background is, so they have a little bit more noise compared to a PMT. So that doesn't help. There are also some other issues like with crosstalk. So like you can have a SIPM that triggers another one next to it. Another SIPM next to it, kind of, so you have like a higher background compared to maybe a PMT. But with a PMT, what's really nice about that is you have good timing, a good output signal, good multiplication. The only problem is they're very large. They're affected by a magnetic field, and they're affected by a magnetic field, and you also need a high bias voltage for them. So it really just depends on your application. If you need a lot, if you need a lot of photodetectors, maybe a SIPM's right for you. But if you only need one, maybe a PMT's right for you. But also you need to think about your environment, where it's going, and what applications it's going to be used for.
Cool. Then we have time for a last question, and this is actually referring to your project. So when you conduct your research, how do you optimize your detector for milk? So maybe a few words on your milk detector here.
Yeah, okay. So I'm not actually using milk. So what's really cool about the detector I'm working on is traditionally you want a scintillator to be transparent because you need a way to transport that light from your scintillator to your photosensor, whether that be a SIPM or a PMT. But what we're using is a opaque scintillator, so you can think about milk. And what happens is when light's emitted, it creates a light ball. So it's stochastically confined around its origin because light's isotropically emitted. And so what's difficult about this is extracting the light from the detector. And the way we do this is using wavelength shifting fibers, or just think of an optical fiber that are able to absorb that light, re-emit some photons, and then those photons get trapped in a fiber and travel to the ends. And so using the information about the light output from those fibers, you're able to kind of do a center of mass reconstruction and understand where light came from. And so what does this have to do with milk? Well, we need to understand the optical properties of this scintillator in order to properly model light propagation and do event reconstruction, improve our energy resolution, and do energy event topology. And so to understand the optical properties, this is a new type of material, so it's quite expensive and hard to get, but milk's optical properties are already well characterized for the food safety and for food quality and assurance. So there are a couple papers that detail the refractive index, the scattering length, and absorption length of milk. So I'm using it as a test bed before I start moving to these more expensive liquids to characterize.
Very exciting. Thanks again, Sandra, for this great presentation and the discussion. And thanks to everyone for joining us today. that concludes today's session. We will be back tomorrow at the same time when Carrie Ann Wilson will be presenting on nutrient physics and detection. Thanks again for joining, and we hope to see you again tomorrow. Bye.